40,000 light-years from Earth, something is drifting through absolute darkness. Two frozen objects, each larger than our entire solar system, loaded with water, methanol, and the organic building blocks of life. No star formed them. No supernova expelled them. They match nothing in our cosmic catalogue. In February 2025, astronomers published findings that eliminated every known explanation. These objects carry shock signatures from violence that happened somewhere else sometime in the past. They show chemistry that should not exist in isolation. And here is what keeps researchers awake at night. If we found two of them by accident, how many thousands more are drifting unseen through this galaxy, carrying ingredients for life to destinations we cannot predict? Tonight, we investigate what ALMA discovered, why scientists are calling for urgent JUST observations, and what it means if the space between stars is populated by frozen strangers we never knew existed. Before we begin, like and subscribe if this calm, science-driven format resonates with you. Use the hype button if it is available. In the comments, note your location, your current time, and the key question this topic triggers for you. I will address the strongest questions in comments or in a later video. The accidental discovery. In 2021, a Japanese infrared satellite called Akari was doing something profoundly unglamorous. It was surveying the galactic plane, scanning strip after strip of the Milky Way in wavelengths our eyes cannot see, cataloguing sources of heat and light that would otherwise remain invisible. This is the quiet, patient work of modern astronomy. No dramatic countdowns, no breathless announcements, just data accumulating in server farms, waiting for human eyes to notice something strange. And something strange did appear. Two objects separated by only about 3 arc minutes on the sky showed absorption signatures that made no immediate sense. They were soaking up infrared light in patterns that screamed one thing to trained astronomers: ice. Not just water ice, but a cocktail of frozen molecules, carbon dioxide, carbon monoxide, methanol, and something else, a cyanide compound whose precise identity remains uncertain. These are the frozen fingerprints of interstellar chemistry, the kind of icy coatings we expect to find on dust grains deep inside stellar nurseries, those dense cocoons of gas and dust where new stars are born. But here is where the story turns. These two objects were not inside any stellar nursery. They were not embedded in any known molecular cloud. They sat in relative isolation, tens of thousands of light-years away, in a direction toward the crux scutum of our galaxy. Imagine finding a snowman in the middle of the Sahara, perfectly preserved, with no explanation for how it got there or why it has not melted. That is roughly the level of confusion these objects introduced. The Akari team noted the anomaly. They published their findings. And then, as so often happens in science, they waited. Because infrared observations can only tell you so much. To truly understand what these objects were, someone would need to look at them in a completely different way. Someone would need radio eyes. 4 years passed. In April of 2022, the Atacama Large Millimeter Submillimeter Array, known as ALMA, turned its attention to these two peculiar sources. ALMA sits high in the Chilean desert, an array of 66 antennas working in concert to detect radio waves from the coldest and most distant corners of the universe. If infrared light reveals what something is made of, radio waves reveal how it moves, how it behaves, and what invisible gases surround it. The astronomers expected one of two outcomes. If these objects were secretly forming stars, ALMA would detect the telltale molecular emissions of stellar birth, complex organic molecules, outflows of gas, the chaotic chemistry of a system pulling itself together under gravity. Alternatively, if these objects were simply background stars sitting behind a previously undetected molecular cloud, ALMA would see extended emissions of carbon monoxide spreading across the field of view, the signature of a diffuse gas structure. Neither happened. What ALMA found was far stranger. At the exact positions of the two icy objects, compact emissions of carbon monoxide and silicon monoxide appeared. The word compact is critical here. Less than 1 arc-second across. These were not extended clouds. They were tight, concentrated sources of gas intimately associated with the icy bodies themselves. And the silicon monoxide was present in quantities that immediately raised eyebrows. Think about that for a moment. Silicon monoxide is a molecule that, under normal interstellar conditions, does not float freely in space. More than 99% of it remains locked inside dust grains, bound up in the solid mineral structures that make up interstellar particles. The only way to liberate silicon monoxide into the gas phase in significant amounts is through violence, shock waves, collisions, energetic events that shatter dust grains and release their silicon into the surrounding environment. The ratio of silicon monoxide to carbon monoxide in these objects was roughly 1 to 1,000. That might sound small, but in the context of interstellar chemistry, it is enormous. Normal molecular clouds show ratios 1,000,000 times smaller. Something had happened to these objects, something powerful enough to destroy dust and free silicon into the gas, and yet there was no obvious source of that energy anywhere nearby. No supernova remnant, no massive star blasting radiation into the void, no protostellar jet carving through the medium, just two lonely, ice-covered bodies drifting in the dark, carrying the chemical evidence of a violent past. The ALMA data revealed something else that defied expectation. Interstellar icy objects are almost always surrounded by dust. This makes intuitive sense. Ices form on the surfaces of dust grains, so where you find ice, you should find the grains it condensed onto. And dust, when warmed even slightly, glows in far infrared and sub-millimeter wavelengths. It is one of the most reliable signatures in all of astronomy. These two objects showed no such glow. ALMA detected no sub-millimeter continuum emission from them at all. Their energy distribution, the pattern of light they emit across different wavelengths, did not match any known category of interstellar source. Not young stellar objects, not evolved stars losing mass, not background stars dimmed by foreground clouds. The spectral fingerprint was simply wrong, like a song played in a key that does not exist. And then came perhaps the strangest revelation of all. Despite appearing so close together on the sky, despite sharing nearly identical colours and brightness and ice absorption features, these two objects are not related to each other. Their velocities through space are dramatically different. One is moving toward us at roughly 25 kilometers per second. The other is receding at about 30 kilometers per second relative to the local standard of rest. They are kinematically independent, passing through the same patch of sky by pure coincidence, like two ships crossing in the night with no knowledge of each other. This is worth pausing on. The odds of finding two such bizarre objects, both defying classification, both covered in organic bearing ices, both showing evidence of violent shock waves, and yet completely unconnected to each other, purely by chance, are difficult to calculate. Either the universe has played an extraordinary statistical trick, or these objects represent something more common than we realized, a population of wandering icy bodies that we're only now learning to see. The research team, led by Takashi Shimonishi of Niigata University, published their findings in the Astrophysical Journal in February of 2025. Their conclusion was cautious but provocative. These objects, they wrote, may represent a new class of interstellar icy objects that provide an environment conducive to the formation of ices and organic molecules. A new class. In astronomy, those words carry weight. They imply that our current taxonomy of the cosmos is incomplete, that there are things drifting between the stars that we have not yet named. Think about what that means for a moment. We have spent decades studying the universe, building ever more powerful telescopes, mapping billions of galaxies, detecting thousands of exoplanets, and yet here, floating in our own galactic backyard, are objects that do not fit any category we have created. Objects rich in the very molecules that form the basis of life as we know it. Objects that have been shaped by energetic processes we cannot yet identify. Objects that exist in isolation, far from the stellar nurseries where we expected such chemistry to occur. The discovery raises questions that ripple outward in every direction. Where did these objects come from? What created them? How many more are out there, invisible to our current surveys, carrying frozen reservoirs of organic potential through the emptiness between stars? And perhaps most haunting of all, what role might such wanderers play in the story of life itself? We are taught that the ingredients for life form in specific places, in the dense cores of molecular clouds, in the warm inner regions of protoplanetary disks, on the surfaces of comets and asteroids within young solar systems. But if organic bearing ices can exist in isolation, far from any star, drifting for billions of years through the galactic void, then the chemistry of life may be far more distributed than we imagined. The seeds may be everywhere, scattered across the galaxy like pollen on the wind, waiting for the right conditions to take root. Consider the timeline of this discovery. 4 years elapsed between Akari's initial detection and ALMA's follow-up observations. 4 years during which these objects continued their silent journey through the galaxy, indifferent to our growing curiosity. In astronomical terms, 4 years is nothing. These objects have likely been travelling for millions, perhaps billions of years. They carry within their frozen chemistry a record of events we can barely imagine, collisions and formations and transformations that occurred when our own solar system was young, or perhaps before it even existed. The sheer scale of distances involved deserves attention. These objects lie between 30,000 and 40,000 light-years from Earth. That means the light we are analysing left those frozen surfaces before modern humans had developed writing, before agriculture, before the first cities rose along the banks of the Tigris and Euphrates. We are looking at ancient messengers, and yet their message remains encrypted in molecular signatures we are only beginning to decode. What strikes many researchers is not just what was found, but what was missing. No thermal emission from warm dust. No extended gas structures suggesting a parent cloud. No stellar companion providing energy or gravitational anchor. These objects appear genuinely alone, suspended in the void between star systems, carrying their burden of ice and organics through a medium so sparse that a cubic centimetre contains only a handful of atoms. In such emptiness, chemistry should grind to a halt. Reactions require collisions, and collisions require neighbours. Yet here we have objects rich in complex molecules, formed under conditions we do not understand, preserved by processes we cannot yet name. The team at Niigata University was careful to rule out alternative explanations. Could these be distant background galaxies mimicking the signatures of icy objects? The velocity measurements said, no. The spectral features were too specific, too characteristic of interstellar ice chemistry. Could they be unusual variable stars undergoing rare outbursts? Again, the evidence pointed elsewhere. The lack of sub-millimetre continuum, the compact gas emissions, the high silicon monoxide abundance, none of these fit any known stellar phenomenon. One by one, the familiar categories were tested and found wanting. What remains is a genuine anomaly. And in science, anomalies are precious. They are the cracks in our understanding through which new knowledge enters. Every major revolution in astronomy has begun with an observation that did not fit, a measurement that refused to obey the rules. Pulsars were discovered because Jocelyn Bell noticed a strange repeating signal that her supervisors initially dismissed as interference. Gamma-ray bursts were found by satellites designed to detect nuclear weapons tests. The accelerating expansion of the universe was revealed by supernovae that were dimmer than they should have been. In each case, the anomaly was not a mistake to be explained away, but a messenger carrying news of something fundamental. These two icy objects may be such messengers, or they may turn out to have a mundane explanation that simply eluded the initial analysis. Science does not guarantee revelations, but it does guarantee that the question will be pursued, that telescopes will continue to watch, that theorists will continue to model, and that eventually, one way or another, we will understand what we are looking at. The Akari satellite that first spotted these objects has long since completed its mission. It launched in 2006 and operated until 2011, its cryogenic coolant eventually exhausted, its infrared eyes going dark. But the data it collected lives on, archived and searchable, a treasure trove that continues to yield surprises more than a decade later. This is a reminder that discoveries do not always arrive with fanfare. Sometimes they sit quietly in databases, waiting for someone to ask the right question. Takashi Shimonishi and his colleagues asked that question. And in doing so, they opened a door we did not know existed. Behind that door lies a mystery that touches on the deepest questions we can ask about our place in the universe. Where do the building blocks of life come from? How do they travel? And what does it mean that two frozen strangers, loaded with organic molecules and scarred by ancient violence, can drift unnoticed through the galaxy until a small infrared satellite happens to glance in their direction? The answers are not yet clear, but the search for them has only just begun, and the tools we need to continue that search are already turning their gaze toward these enigmatic wanderers. What they found, and what they did not. When the ALMA data arrived in the spring of 2022, the research team gathered to examine what 66 antennas in the Chilean desert had revealed. They were looking at 2 points in the sky, 2 sources of infrared absorption that had puzzled astronomers for years. The question was simple. What are these things? The answer, it turned out, was anything but. Let us begin with what was detected. At the precise locations of both objects, ALMA picked up emission lines from carbon monoxide and silicon monoxide. These molecules were radiating at specific frequencies, fingerprints as unique as any barcode. Carbon monoxide is one of the most common molecules in the universe after hydrogen. It forms easily, survives well, and glows brightly in radio wavelengths. Finding it was not surprising. What was surprising was how little of it there was, and how tightly concentrated. The carbon monoxide emission from both objects occupied less than 1 arcsecond of sky. To put that in perspective, the full moon spans about 1800 arcseconds. 1 arcsecond is a sliver so thin that most amateur telescopes cannot resolve it. For a gas cloud to appear that compact at a distance of 30 to 40,000 light-years means the actual physical size of these structures is remarkably small. The team calculated dimensions between 100 and 1,000 astronomical units. That is roughly the scale of a large solar system, perhaps stretching from a central point to the outer reaches of a Kuiper belt analogue. In the context of interstellar clouds, which typically span light-years, this is minuscule. These are not sprawling nebulae. They are tight, dense, isolated pockets of matter. The silicon monoxide detection was more provocative. This molecule does not form under gentle conditions. In the quiet cold of interstellar space, silicon atoms remain locked inside solid grains, bound into silicate minerals that make up the rocky cores of cosmic dust. To free silicon and allow it to bond with oxygen in the gas phase requires energy. Significant energy. The kind of energy released when shockwaves tear through a medium at tens of kilometers per second, sputtering atoms off grain surfaces and shattering the particles themselves. Both objects showed silicon monoxide abundances that were, by normal standards, extreme. The ratio of silicon monoxide to carbon monoxide hovered around 1 part in 1,000. In typical molecular clouds, this ratio is closer to 1 part in 1,000,000,000. Something had amplified the silicon monoxide signal by a factor of roughly 1,000,000. Something violent had occurred in the vicinity of these objects, or perhaps to the objects themselves. The evidence pointed towards shocks, but shocks require a source. A supernova blast wave, a stellar wind, a protostellar jet, a collision between clouds. None of these were present. The objects sat in isolation, bearing the chemical scars of violence without any obvious perpetrator. The line widths added another layer to the puzzle. When gas moves, the light it emits gets shifted in frequency. Gas moving toward us appears bluer, gas moving away appears redder. If a cloud of gas contains material moving at many different speeds, the emission line broadens, smeared out by the range of velocities. Both objects showed line widths between 8 and 14 kilometers per second. This is not the gentle thermal motion of cold gas. This is turbulent dynamic motion, the kind associated with outflows, shocks, or rapid expansion. Yet again, there was no visible driver. The gas was disturbed, but by what? Now consider what ALMA did not detect. This absence is perhaps more significant than any presence. Interstellar icy objects are, almost without exception, embedded in dust. This is not a coincidence. It is a consequence of how interstellar ice forms. In the cold, dense regions of the galaxy, atoms and small molecules drift through space until they encounter a dust grain. The grain acts as a surface, a meeting place where atoms can stick and react. Water forms when oxygen meets hydrogen on a grain surface. Carbon dioxide forms when carbon monoxide meets oxygen. Methanol forms through hydrogenation of carbon monoxide. Layer by layer, an icy mantle builds up around the dust grain, a frozen shell of volatile compounds wrapped around a rocky or carbonate core. Because of this intimate relationship, wherever we find interstellar ice, we expect to find the dust it formed on. Dust grains, when warmed even slightly by nearby stars or by the faint glow of the cosmic microwave background, emit thermal radiation in the far infrared and submillimeter wavelengths. This emission is one of the most reliable tracers in all of astronomy. Point a submillimeter telescope at a molecular cloud, and you will see dust glowing softly in the cold. ALMA pointed at these 2 icy objects and saw nothing. No continuum emission, no thermal glow. The dust that should have been there, the very substrate on which the detected ices must have formed, was absent from the submillimeter data. This is deeply strange. It is like finding a snowball with no rock at its centre, or a pearl with no grain of sand to nucleate it. The ice exists. The infrared absorption features prove it beyond doubt. Water ice, carbon dioxide ice, carbon monoxide ice, methanol ice, and cyanate compounds are all present in significant abundances, but the dust that should accompany them has either been destroyed, dispersed, or was never there in the first place. The team considered every known category of interstellar object and found that none could account for this combination of features. Young stellar objects, protostars still gathering mass from their surrounding envelopes, show deep ice absorption, but they also show strong submillimeter emission from the dust in their envelopes. Their spectral energy distributions peak in the far infrared, not at 5 micrometers as these objects do. They are embedded in larger cloud structures, connected to the galactic ecology of star formation. These two objects match none of those criteria. Evolved stars, red giants, and asymptotic giant branch stars shedding their outer layers can also show ice features. But these stars are losing mass outward, creating expanding shells of gas and dust that glow brightly at long wavelengths. Their spectra are dominated by emission, not absorption, and they are, by definition, associated with a central star. These two objects have no such star. There is no luminous source at their centres, no engine driving a stellar wind. Background stars seen through dense molecular clouds can display ice absorption features. The intervening cloud imprints its chemical signature on the light passing through, but in such cases the cloud itself would be visible. ALMA would detect extended carbon monoxide emission, the telltale sign of a foreground molecular structure. No such extended emission was found. The carbon monoxide is compact, localized, bound to the objects themselves, not spread across a diffuse cloud. Comets, at least the comets we know from our own solar system, are icy bodies rich in volatile compounds. But comets are small, typically a few kilometers across, and they orbit stars. They become visible when they approach their parent star and begin to outgas, forming the spectacular tails that have captivated humans for millennia. These objects are not comets in any conventional sense. They are thousands of astronomical units in size, orders of magnitude larger than any comet we have ever observed, and they are not orbiting anything. They drift through interstellar space, unbound to any stellar system. Rogue planets, worlds ejected from their birth systems and wandering the galaxy in darkness, represent another category of isolated object. But rogue planets are solid bodies, perhaps with atmospheres, perhaps with subsurface oceans kept liquid by internal heat. They do not show the absorption signatures of interstellar ices. They do not emit silicon monoxide. They are not surrounded by compact envelopes of gas bearing the chemical fingerprints of shocks. One by one, the familiar classifications fail. The objects do not fit, and when an observation does not fit any existing category, astronomers are left with two possibilities. Either the observation is flawed, or the categories are incomplete. The observation is not flawed. ALMA is one of the most precise instruments ever built. Its data have been verified, cross-checked, and analysed by multiple independent researchers. The detections are real. The abundances are accurate. The velocities are measured to within fractions of a kilometre per second. If there is an error, it lies not in the data but in our expectations, which brings us to the second possibility. Our categories are incomplete. There exists, somewhere in the taxonomy of the cosmos, a box we have not yet built, a label we have not yet written, a class of object that can possess deep ice absorption, compact gas emission, extreme silicon monoxide abundance, broad line widths indicative of shocks, no submillimeter dust continuum, no association with star-forming regions, no connection to any stellar system, and a size scale intermediate between comets and molecular clouds. Such objects, if they exist in numbers, have escaped our notice until now. They have drifted through the galaxy for eons, carrying their frozen chemistry in silence, invisible to surveys that were not designed to find them. The Akari satellite stumbled upon two of them by accident. ALMA confirmed their strangeness. And now the question shifts from what are they to how many are there? If two such objects can be found in a single infrared survey of the galactic plane, how many more lie hidden in archival data, waiting to be recognized? How many drift through regions of the sky that no telescope has examined with sufficient sensitivity? The galaxy is vast. Our surveys, for all their ambition, cover only a fraction of it. The population of these wandering icy bodies could number in the thousands, the millions, or more. We simply do not know. What we do know is that the molecules detected in these objects are not random. Water, carbon dioxide, carbon monoxide, methanol, cyanate compounds, these are the building blocks of prebiotic chemistry. These are the ingredients that, under the right conditions, can combine to form amino acids, nucleotides, the scaffolding of life. Finding them in the frozen cores of molecular clouds is expected. Finding them drifting alone through interstellar space far from any nurturing star is something else entirely. It suggests that the raw materials for life are more mobile, more resilient, more widely distributed than we assumed. It suggests that the galaxy may be seeded with organic potential in ways we are only beginning to appreciate. There is another detail worth lingering on. The two objects, despite their apparent similarity, are moving in completely different directions at completely different speeds. Object 1 has a systemic velocity of roughly negative 27 kilometers per second. Object 2 moves at roughly positive 31 kilometers per second. These are not small differences. These are dramatically divergent trajectories, proving beyond doubt that these two bodies are not companions, not fragments of a single parent object, not members of a common stream. They are strangers passing through the same region of sky by pure cosmic coincidence. And yet they share so many characteristics. Both show deep ice absorption, both emit compact silicon monoxide, both lack submillimeter dust continuum, both have spectral energy distributions that peak near 5 micrometers, both defy classification. The probability of finding two such rare objects in the same small patch of sky, purely by chance, seems vanishingly small, unless, of course, they are not rare at all, unless these objects represent a common but previously unrecognized population scattered throughout the galactic disk in numbers large enough that finding two in close proximity is unremarkable. This is the possibility that haunts the edges of the discovery. What if we have been blind to an entire class of cosmic wanderer? What if the galaxy is filled with frozen messengers carrying organic chemistry through the void, and we simply lack the tools or the inclination to see them? The Akari survey was not designed to find such objects. It was a general-purpose infrared survey, casting a wide net across the galactic plane. These two detections were accidents, anomalies flagged for follow-up because they did not fit. How many others slipped through, dismissed as noise or filed away as unclassifiable? The search for answers continues, but the questions have already changed. We are no longer simply asking what these objects are. We are asking what their existence means for the story of life itself, and how many silent travellers share the galaxy with us, drifting unseen through the dark. The silicon monoxide paradox. Silicon is one of the most abundant elements in the universe. It ranks 8th on the cosmic inventory, forged in the cores of massive stars and scattered across galaxies by supernova explosions. On Earth, silicon forms the backbone of rocks and sand, the crystals in our computer chips, the glass in our windows. In space, it plays an equally fundamental role. Silicon atoms combine with oxygen and magnesium to form silicate minerals, the tiny grains of cosmic dust that drift through interstellar clouds and eventually coalesce into planets, moons, and asteroids. But here is the paradox. Despite silicon's abundance, its monoxide form is extraordinarily rare in the gas phase of interstellar space. Under normal conditions, more than 99.9% of all silicon remains locked inside solid dust grains. It does not float freely. It does not radiate detectable emission lines. It sits imprisoned in mineral lattices, invisible to radio telescopes, participating in chemistry only at the surfaces of grains where it can interact with passing atoms. To liberate silicon monoxide into the gas phase requires violence. Shockwaves travelling at speeds exceeding 10 kilometers per second can sputter atoms off grain surfaces, knocking silicon loose through kinetic impacts. Faster shocks, those approaching 50 or 100 kilometers per second, can shatter grains entirely, vaporizing their mineral content and releasing silicon in enormous quantities. Intense ultraviolet radiation from nearby massive stars can also photodesorb silicon from grain surfaces, though this process is less efficient than shock destruction. The two mysterious icy objects discovered by Akari and observed by ALMA show silicon monoxide abundances that are, by any standard, extreme. The ratio of silicon monoxide to carbon monoxide in these objects hovers around 1 part in 1,000. To appreciate how anomalous this is, consider that in quiescent molecular clouds, clouds that are simply drifting through space without any energetic disturbance, this ratio typically falls below 1 part in a billion. The objects show silicon monoxide enrichment by a factor of roughly 1 million compared to undisturbed interstellar material. This is not a subtle enhancement. This is a screaming chemical signature of shock processing. Somewhere, at some time, these objects experience conditions violent enough to destroy a significant fraction of their dust content and release silicon into the surrounding gas. The evidence is written in the molecular abundances as clearly as a fingerprint at a crime scene. But like a crime scene found years after the event, the perpetrator is nowhere to be seen. Consider the usual suspects. Supernova remnants are among the most powerful shock generators in the galaxy. When a massive star explodes, it sends a blast wave racing outward at thousands of kilometers per second. This wave sweeps up interstellar material, compresses it, heats it, and processes it chemically. Silicon monoxide emission is commonly observed in supernova remnants precisely because the shocks are powerful enough to destroy dust on a massive scale. But these two icy objects are not located within any known supernova remnant. They do not lie along the expanding shells of ancient explosions. They show no excess of other shock traces that would indicate recent interaction with a blast wave. If a supernova was responsible for their silicon monoxide enrichment, it must have occurred long ago, and the remnant has since dispersed beyond recognition. The objects would be carrying the chemical memory of an event that left no other visible trace. Protostellar outflows represent another common source of interstellar shocks. When a young star forms, it often drives powerful jets of material perpendicular to its accretion disk. These jets plough into the surrounding cloud, creating bow shocks that can reach velocities of hundreds of kilometers per second. Silicon monoxide emission is a classic tracer of such outflows, lighting up the regions where jets collide with ambient gas. But these objects are not associated with any star-forming region. They lie in isolation, tens of thousands of light-years from the nearest known stellar nursery. There is no protostar at their centers. There is no accretion disk. There are no jets. If protostellar activity once occurred here, it has long since ceased, and the parent star has either died or drifted away, leaving behind only these frozen, shock-processed remnants. Cloud collisions offer a third possibility. When molecular clouds collide, the impact zone can generate shocks sufficient to process dust and enhance silicon monoxide abundances. Such collisions are not rare in the galaxy. The interstellar medium is dynamic, with clouds moving at tens of kilometers per second relative to one another. Convergent flows, spiral arm passages, and gravitational interactions can all bring clouds into contact, triggering shocks at the interface. Yet once, again, the evidence does not quite fit. Cloud collisions produce extended shock zones, regions of enhanced emission that span light years. The silicon monoxide in these objects is compact, confined to structures only hundreds to 1,000 astronomical units across. If a cloud collision was responsible, it would have to be an extraordinarily localized event, a glancing blow that processed only a tiny pocket of material while leaving the surrounding medium undisturbed. There is another possibility, one that the research team raised cautiously in their published analysis. What if the shocks are not external at all? What if the objects themselves are the source of their own violence? Consider a scenario in which these objects are not static clouds but dynamic structures, perhaps edge-on-disk systems seen from a particular angle, or compact nebulae surrounding hidden energy sources. In such cases, internal processes could generate the shocks needed to liberate silicon monoxide. Accretion onto a central object, even a very low-mass one, could drive outflows. Collisions between clumps within the structure could create localized shock zones. Magnetic reconnection events could release bursts of energy sufficient to process dust. The problem is that no such central object has been detected. ALMA saw no continuum emission from a compact source. Infrared observations show no embedded protostar. If there is an engine at the heart of these objects, it is either extraordinarily faint or extraordinarily well hidden. The energy budget simply does not add up. Something powerful enough to generate shock velocities of 10 to 50 kilometers per second should leave other traces, thermal emission, outflow signatures, variability. None have been observed. This brings us to perhaps the most unsettling interpretation. What if the shocks occurred long ago in a different location, and the objects have simply been carrying their chemical enrichment ever since? Think about what this would mean. An icy body, born in some violent corner of the galaxy, processed by shocks during its formation or early evolution, ejected or drifting into interstellar space, and travelling for millions or billions of years while preserving the chemical record of its traumatic origin. The silicon monoxide we detect today would be a fossil signature, a molecular memory of events that transpired when the galaxy was younger, when stellar populations were different, when the interstellar medium had a different structure and composition. In the cold of interstellar space, chemistry slows to a crawl. Reactions that would proceed in milliseconds at room temperature can take millions of years when the temperature hovers just a few degrees above absolute zero. Molecules that formed in ancient shocks might persist indefinitely, frozen in place, waiting for a telescope sensitive enough to detect their faint emissions. These objects could be time capsules, preserving information about conditions that no longer exist anywhere in the observable galaxy. There is a poetic dimension to this possibility. We are accustomed to thinking of astronomy as the study of light, and light, of course, is old. The photons reaching us from a distant galaxy left their source millions of years ago. We see the past simply by looking outward, but these objects offer a different kind of temporal window. Their chemistry encodes history in molecular abundances rather than photons. The silicon monoxide ratio tells us about shocks that occurred in a place and time we cannot directly observe. The ice features tell us about condensation processes that played out under conditions we can only model. The objects are archives, drifting libraries written in the language of astrochemistry. The line widths add another clue. Both objects show carbon monoxide and silicon monoxide emission, with velocity spreads of 8 to 14 kilometers per second. This is broader than thermal line widths, which would be only a fraction of a kilometer per second at the temperatures of cold interstellar gas. The broadening indicates bulk motion, turbulence, or unresolved velocity gradients within the emitting region. Something is stirring the gas, even now, even after whatever ancient event produced the silicon monoxide enrichment. One possibility is that the objects are still dynamically active, that internal motions continue to agitate the gas on timescales of thousands or millions of years. Another is that we are seeing the signature of expansion, material still coasting outward from a central disturbance, gradually slowing as it interacts with the ambient medium. A third is that the broad lines reflect the presence of multiple components along the line of sight, distinct clumps with different velocities superposed in our observations. Untangling these possibilities will require higher resolution observations, spectroscopy that can resolve the internal structure of the gas, and determine whether the broadening is due to coherent motion or random turbulence. The James Webb Space Telescope and Futurama campaigns may provide such resolution, revealing the internal kinematics of these enigmatic objects for the first time. But regardless of the mechanism, the silicon monoxide paradox remains. These objects contain a molecule that should not be there, at least not in the quantities observed. The only known way to produce such enrichment is through shock processing, yet no shock source is evident. Either we are missing something in our observations, or these objects carry the signature of events that occurred elsewhere, long ago, in a chapter of galactic history that we cannot directly access. The universe keeps records in strange ways. Ice preserves organic molecules, silicon monoxide preserves the memory of violence, and two lonely objects drifting through the dark carry testimony of processes we are only beginning to understand. Whatever created them, whatever processed them, whatever launched them on their current trajectories, left a chemical signature that has survived across cosmic time. We are reading that signature now 30,000 light-years away, millions of years after the fact, and finding that it asks more questions than it answers. The investigation continues, as it must. But the silicon monoxide paradox has already taught us something valuable. It has taught us that the interstellar medium is not a passive backdrop to stellar evolution. It is an active, dynamic environment where chemistry and physics intertwine in ways we are still mapping. And it has taught us that objects can carry their histories with them, molecular diaries written in isotopes and abundances, waiting for someone to learn how to read them. There is one more dimension to consider. The detection of silicon monoxide at such elevated levels suggests that these objects may represent a transitional state, a phase in the evolution of interstellar material that we have not previously captured. Most of our observations catch clouds either before processing when they are quiescent and silicon remains locked in grains, or long after, when shock-processed material has dispersed and mixed back into the general interstellar medium. These objects might represent the intermediate stage, the frozen aftermath of violence before dilution erases the evidence. If that interpretation is correct, then finding more such objects becomes critically important. Each one would offer a snapshot of shock chemistry, a data point in the timeline of how interstellar material evolves. By comparing the abundances and kinematics of multiple objects, astronomers could begin to reconstruct the sequence of events, to understand how long silicon monoxide persists after its liberation, how it eventually returns to dust grains, and what other chemical transformations accompany these processes. The implications extend beyond mere curiosity. Understanding shock chemistry is essential for tracing the flow of matter through galaxies, from stellar nurseries to planetary systems. The SphereX mission, launched in March of 2025, may help. Its all-sky infrared survey is specifically designed to detect interstellar ices across the Milky Way. If objects like these exist in significant numbers, SphereX has the sensitivity to find them, and with each new detection, the silicon monoxide paradox will become less paradoxical and more instructive, a window into the violent heart of interstellar chemistry that we are only now learning to open. What we find there may reshape our understanding of how the galaxy processes its raw materials and how the ingredients of life travel from their violent birthplaces to the quiet surfaces of young planets, orphans of the galaxy. There is a loneliness to these objects that transcends scientific description. They drift through a region of space that contains, on average, less than 1 atom per cubic centimetre. To call this environment empty would be an understatement. It is a vacuum more perfect than anything we can create in laboratories on Earth, a void so absolute that light itself takes thousands of years to cross it. And somewhere in that void, 2 frozen bodies loaded with organic molecules continue their silent journey, bound to nothing, belonging to no one. The concept of orphaned objects in space is not new. Astronomers have long known that the galaxy contains wanderers, bodies that have been ejected from their birth systems or that formed in isolation without ever joining a stellar family. Rogue planets number in the billions, perhaps the trillions, drifting between stars in eternal darkness. Comets that once orbited distant suns have been flung into interstellar space by gravitational interactions, carrying their ices across light years. Even stars themselves can become orphans, ejected from clusters and associations to travel alone through the galactic disk. But these 2 icy objects represent something different. They are not planets, at least not in any recognizable sense. They lack the mass, the compactness, the solid cores that define planetary bodies. They are not comets, whose icy nuclei rarely exceed a few tens of kilometers in diameter. They are not failed stars or brown dwarfs, which would show thermal emission from their contracting cores. They occupy a strange middle ground, structures hundreds to thousands of astronomical units across, rich in ices and gas, processed by shocks, and utterly alone. The distances involved are staggering. These objects lie between 30,000 and 40,000 light-years from Earth. For reference, the centre of the Milky Way is about 26,000 light-years away. These wanderers inhabit the outer reaches of the galactic disk, in a region where stars are sparser and the interstellar medium thins toward the intergalactic void. They are far from the spiral arms where most star formation occurs, far from the dense molecular clouds where ices typically reside. They have travelled to a cosmic suburb, or perhaps they were born there in conditions we do not yet understand. How does an object like this come to exist in such isolation? The possibilities fall into a few broad categories, each with its own implications for what these objects truly are. The first possibility is ejection. The object formed as part of a larger system, perhaps a protoplanetary disk around a young star, and was subsequently expelled by gravitational interactions. In the chaotic early stages of planetary system formation, close encounters between massive planets can launch smaller bodies onto escape trajectories. The same process that populates our own Oort cloud with icy comets could, in principle, send larger structures careening into interstellar space. If the ejection occurred early enough, before the object had fully collapsed into a compact body, it might retain the extended diffuse structure we observe today. This scenario has precedent. The interstellar object Oumuamua, detected passing through our solar system in 2017, was almost certainly ejected from another star system. Its elongated shape and peculiar acceleration suggested a composition rich in frozen nitrogen or hydrogen, materials that sublimated as it passed close to the Sun and gave it a gentle push. The comet Borisov, detected in 2019, showed a more conventional cometary composition, but travelled on a clearly interstellar trajectory. These objects proved that material can and does escape from stellar systems to wander the galaxy. But Oumuamua was perhaps a few hundred metres long. Borisov was a few kilometres across. The objects detected by Akari and ALMA are orders of magnitude larger, spanning hundreds to 1,000 astronomical units. Ejecting something that size requires extraordinary circumstances, perhaps the complete dispersal of a protoplanetary disk before it could collapse into planets, or the violent disruption of an entire stellar system by a close encounter with another star. Such events are not impossible, but they are rare. If these objects formed through ejection, they represent the survivors of catastrophic processes that destroy most of the system from which they came. The second possibility is in situ formation. The object never belonged to a stellar system at all. It formed directly from the interstellar medium, condensing out of a small, dense pocket of gas and dust that never achieved the mass necessary to ignite a star. Brown dwarfs form this way, collapsing from molecular cloud cores that are too small to produce main-sequence stars. Sub-brown dwarf objects, sometimes called planemos, or planetary mass objects, represent the lower end of this spectrum, bodies with masses below the deuterium burning limit that form in isolation rather than in circumstellar disks. Could these icy objects be related to such isolated formation events? The presence of interstellar ices suggests that they spent time in a cold, dense environment, where atoms could freeze onto grain surfaces. The detection of shocked gas suggests that they experienced some kind of energetic processing, perhaps during their formation, or shortly thereafter. If they formed in isolation, they might represent a population of objects that has existed since the early days of the galaxy, drifting through space for billions of years, carrying the primordial chemistry of their birthplaces. This interpretation raises its own questions. Isolated formation typically produces compact objects, not extended structures spanning hundreds of astronomical units. The cores that give rise to brown dwarfs and planemos are themselves only thousands of astronomical units across, and they collapse dramatically during the formation process. To end up with an extended structure, the object would need to have avoided significant collapse, perhaps because it lacked sufficient mass or because it was disrupted before collapse could proceed. The physics of such arrested development are not well understood. The third possibility is catastrophic origin. The object is not a pristine remnant of the early galaxy, but the debris of a violent event, the shrapnel from a collision or explosion that scattered material into interstellar space. Planetary collisions, though rare, do occur. The Moon is thought to have formed from the debris of a giant impact between the early Earth and a Mars-sized body. Similar collisions could occur in other systems, and if they happen at high enough velocity, some of the debris might escape the system entirely. Stellar collisions and mergers are another potential source. When two stars collide, whether through dynamical encounters in dense clusters or through the death spiral of a binary system, enormous amounts of material can be ejected. The Blue Ring Nebula, studied extensively over the past several years, is thought to be the remnant of such a stellar merger, a cloud of debris expelled when two stars combined into one. Could these icy objects be fragments of a similar event, processed by the shocks of the merger itself and flung into the galaxy to wander forever? There is no way to determine, from current data, which of these scenarios applies. The objects do not carry labels indicating their origin. They simply exist, drifting through the dark, offering only their chemical and kinematic signatures as clues. But each possibility has implications for how common such objects might be. If they form through ejection, their abundance depends on how often stellar systems experience the kind of violent reshuffling that can expel large structures. If they form in situ, their abundance depends on the frequency of low-mass cloud cores that fail to produce stars. If they form through catastrophic events, their abundance depends on the rate of collisions and mergers in the galaxy. In each case, finding two such objects in a single infrared survey suggests that the underlying process, whatever it is, must be reasonably efficient. Rare objects do not appear in pairs by coincidence. The isolation of these objects also affects their chemistry in ways that are difficult to fully appreciate. In the interstellar medium, chemical reactions proceed through two main pathways. Gas phase reactions occur when molecules collide with each other, exchanging atoms or breaking bonds through energetic impacts. Surface reactions occur when atoms land on dust grains and interact with each other or with the grain material. Both pathways require encounters, and encounters require density. In the space between stars, densities are so low that gas phase reactions grind nearly to a halt. A molecule might travel for years without encountering another molecule. Surface chemistry continues, but only slowly, as the occasional atom drifts onto a grain surface and waits for a reaction partner to arrive. Under these conditions, the chemical composition of an object becomes frozen, locked in place by the absence of reaction partners. Whatever molecular abundances existed when the object entered interstellar space will persist indefinitely, preserved by the very emptiness that surrounds it. This is why the detection of organic molecules in these objects is so significant. Water, methanol, carbon dioxide, carbon monoxide, cyanate compounds, these are not molecules that form easily in the cold void. They are products of active chemistry, processes that require energy, density, and time. Their presence in objects drifting through the most isolated regions of the galaxy tells us that this chemistry occurred somewhere else, in some denser, more active environment, before the objects began their long journey into solitude. The objects are messengers, in other words. They carry chemical information from their birthplaces to the empty reaches of the galaxy, preserving that information across timescales that dwarf human history. By studying their composition, we can learn about environments that no longer exist, reactions that no longer occur, conditions that prevailed in regions of space now dispersed beyond recognition. There is something humbling in this realization. We sit on a small planet orbiting an ordinary star in a middling region of a single galaxy, and yet we can reach out with our instruments and touch the frozen remnants of processes that occurred 40,000 light-years away, millions or billions of years ago. The orphans of the galaxy are not truly alone. They are connected to us through the light they emit and absorb, the molecules they carry, and the questions they inspire. What other orphans drift unseen through the dark? How many frozen messengers carry the chemistry of ancient stellar nurseries through the void? We do not yet know, but the discovery of these two objects suggests that the answer is far more than zero, and perhaps far more than we ever imagined. The implications ripple outward in unexpected directions. If organic-bearing icy objects populate the galaxy in significant numbers, they represent a reservoir of prebiotic chemistry that exists independent of any star. They are not bound to planetary systems. They do not require stellar radiation to form or survive. They simply exist, carrying water and carbon compounds through the emptiness, occasionally passing close enough to other systems to be captured or to deposit their material through collisions. This has consequences for how we think about the distribution of life's ingredients. The traditional view holds that organic molecules form primarily in two places: the dense cores of molecular clouds and the warm inner regions of protoplanetary disks. Both environments are tied to star formation. Both are temporary phases in the evolution of stellar systems. Once the stars form and the disks disperse, the chemistry is locked into planets and small bodies, no longer available to seed new systems. But if wandering icy objects exist in abundance, this picture changes. The organic molecules they carry are mobile, travelling through the galaxy on timescales of millions or billions of years. A body ejected from one stellar system could, in principle, be captured by another, delivering its cargo of ices to a new generation of planets. Even without capture, the passage of such an object through a young system could deposit material, enriching the local inventory of organics through collisions or tidal disruption. The galaxy in this view becomes a vast network of chemical exchange. Stellar nurseries produce organic-bearing objects. Some of those objects remain in their birth systems, becoming comets and asteroids. Others are ejected, joining the population of interstellar wanderers. Over billions of years, these wanderers crisscross the galaxy, occasionally interacting with other systems, spreading their chemical payload. The result is a kind of cosmic cross-pollination, a slow but persistent mixing of organic material across the entire galactic disk. These two lonely objects, drifting in darkness 40,000 light-years away, may be small contributors to this vast process, or they may be exemplars of a population so numerous that its collective contribution shapes the chemistry of every planetary system in the galaxy. We do not know which scenario is correct, but the possibility itself is profound, and the search for more such objects has taken on new urgency. The orphans of the galaxy may not be abandoned after all. They may be travellers, carrying messages written in molecules, connecting distant stellar systems across the gulf of interstellar space. And we are only now learning to read what they have to say. The building blocks of life in exile. The molecules frozen within these objects read like a recipe for something far more profound than simple chemistry. Water, carbon dioxide, carbon monoxide, methanol, cyanate compounds. These are not random assemblages of atoms. These are the precursors, the raw materials, the first steps on a ladder that could, under the right conditions, climb toward the complexity of life. Consider water. On Earth, it is so commonplace that we rarely pause to appreciate its strangeness. A molecule of 2 hydrogen atoms bonded to 1 oxygen atom, it should by all rights be a gas at room temperature, given its low molecular weight. But the polar nature of the water molecule creates hydrogen bonds between neighbours, holding the liquid together against thermal disruption. This same polarity makes water an exceptional solvent, capable of dissolving more substances than any other common liquid. Life as we know it is inseparable from water. Every cell on Earth is a bag of aqueous chemistry, reactions proceeding in a salty solution that has changed remarkably little over 3.5 billion years. Finding water ice in interstellar space is not unusual. Water is one of the most abundant molecules in the universe, formed easily when hydrogen meets oxygen on the surfaces of dust grains. What is unusual is finding it in objects that exist far from any star-forming region, drifting through the emptiest reaches of the galaxy. The water in these objects was not formed in place. It was formed somewhere else, in some denser environment, and has survived the journey into isolation. The ice is ancient, a frozen relic of chemistry that occurred before these objects began their long drift through the void. Now consider the carbon compounds. Carbon dioxide, carbon monoxide, methanol and cyanate compounds all share one critical feature. They contain carbon atoms bonded to other elements in configurations that can serve as starting points for more complex molecules. Carbon is unique among the elements in its ability to form stable bonds with itself and with many other atoms, creating chains and rings and networks of arbitrary complexity. This versatility makes carbon the backbone of organic chemistry, the chemistry of life. Methanol deserves particular attention. A single carbon atom bonded to 3 hydrogens and 1 hydroxyl group. Methanol is among the simplest organic molecules, but simplicity belies importance. Methanol participates in reactions that can produce larger organic compounds, including formaldehyde, formic acid, and ultimately amino acids. In the warm inner regions of protoplanetary disks, methanol ice sublimates and drives a cascade of gas phase chemistry that builds molecular complexity. Finding methanol in these isolated objects suggests that at least the first steps of this cascade have already occurred, locked in place by the cold, waiting to resume if the objects ever find themselves in a warmer environment. The cyanate compounds are perhaps the most intriguing. The cyanate group consists of carbon, nitrogen, and oxygen, bonded in a specific arrangement. Cyanate chemistry connects to some of the most important pathways in prebiotic synthesis. Hydrogen cyanide, a related compound, is thought to play a crucial role in the formation of nucleobases, the information-carrying components of DNA and RNA. Finding cyanate-bearing molecules in interstellar ices suggests that the chemistry leading toward genetic material can begin in space, long before any planet exists to host it. This is the heart of the discovery's significance. The molecules in these objects are not merely interesting, they are relevant. They connect directly to the question of how life began, not on Earth specifically, but anywhere in the universe. If the building blocks of life can form in interstellar environments and survive transport across the galaxy, then the raw materials for biology are not confined to the surfaces of planets. They are distributed, mobile, available wherever chance might deliver them. The idea that life's ingredients have cosmic origins is not new. Since the 1950s, scientists have recognized that organic molecules can form in space and be delivered to planets via comets, and meteorites. The Murchison meteorite, which fell in Australia in 1969, contained over 90 different amino acids, many of which are not found in terrestrial biology. The Rosetta mission to Comet 67 P. Churyumov-Gerasimenko detected glycine, the simplest amino acid, in the comet's coma. The evidence for extraterrestrial organics has grown steadily over the decades, to the point where few scientists doubt that Earth received a significant portion of its organic inventory from space. But there is a difference between recognizing that space contains organic molecules and understanding where those molecules form and how they travel. The traditional view placed organic synthesis primarily in two locations: the dense cores of molecular clouds, where cold chemistry on grain surfaces builds molecules atom by atom, and the warm regions around young stars, where radiation and heat drive more energetic reactions. Both locations are tied to the star formation process. Both are transient phases, lasting only a few million years before dispersing or evolving into something else. The discovery of organic-bearing icy objects in interstellar isolation challenges this picture. These objects exist far from any star-forming region. They show no association with molecular clouds or stellar nurseries, yet they carry the same chemical signatures we expect from active sites of organic synthesis. Either they formed in such environments and were subsequently ejected, carrying their chemical cargo with them, or there exist pathways for organic chemistry that we have not yet recognized, processes that can operate in the cold, sparse conditions of interstellar space itself. The first possibility is already transformative. If objects can be ejected from stellar nurseries with their organic ices intact, then those ices can travel for billions of years, crossing the galaxy, potentially being captured by other stellar systems, or depositing their material through collisions. The organics formed in one nursery become available to planetary systems forming in entirely different regions of space, millions or billions of years later. The galaxy becomes a network of organic exchange, with stellar nurseries serving as production sites and wandering icy objects serving as delivery vehicles. The second possibility is more speculative but equally profound. Could organic chemistry proceed in the interstellar medium itself, far from any stellar energy source? The answer depends on what processes can substitute for stellar radiation in driving chemical reactions. Cosmic rays, high-energy particles that permeate the galaxy, can penetrate deep into icy mantles and trigger reactions through ionization and dissociation. Ultraviolet photons from the diffuse interstellar radiation field, though far weaker than stellar radiation, can still induce photochemistry over long timescales. Even the radioactive decay of elements within dust grains can release energy, sufficient to drive local reactions. Laboratory experiments have shown that ice mixtures exposed to simulated cosmic ray bombardment can produce complex organic molecules, including amino acids and nucleobases. The same is true for ultraviolet irradiation of ices. If these processes operate continuously over billions of years, the cumulative effect could be significant. An icy object drifting through interstellar space is not chemically inert. It is slowly cooking, its frozen ingredients transforming under the constant drizzle of cosmic rays and photons into ever more complex products. This picture suggests that the galaxy may be slowly aging its organic chemistry, like wine maturing in a cellar. Objects ejected from stellar nurseries with simple organic ices could develop more complex molecular inventories as they travel, arriving at new planetary systems with a richer chemical payload than they originally carried. The journey itself becomes part of the synthesis, the interstellar medium serving as a kind of slow cooker for prebiotic chemistry. There is a profound implication here for the question of life's origins. If organic molecules are not merely delivered to planets but actively synthesized and processed during interstellar transit, then every planet in the galaxy has access to a cosmic supply chain of prebiotic material. The raw ingredients for life are not accidents of local chemistry. They are products of galactic-scale processes, refined over timescales that dwarf the age of any individual planetary system. This does not guarantee that life will arise wherever these ingredients land. The transition from organic chemistry to living chemistry remains poorly understood, a gap in our knowledge that no amount of interstellar synthesis can fill. But it does change the odds. It suggests that the starting materials for life are universally available, that no planet need bootstrap its own organic inventory from scratch, that the cosmos itself has been preparing the ingredients for biology since the earliest generations of stars. The two objects detected by Akari and ALMA are small samples of a potentially vast population. If such objects are common, the galaxy is seeded with organic potential in ways we're only beginning to appreciate. Every cubic parsec of interstellar space might contain dozens or hundreds of frozen bodies, each carrying water and carbon compounds, each a potential contributor to the chemistry of any planetary system they encounter. We stand at the threshold of a new understanding. The building blocks of life are not confined to planets. They drift between the stars, preserved in ice, shaped by cosmic rays, waiting for circumstances to bring them into contact with worlds where the next steps of the journey can unfold. The exiles carry seeds, and the seeds carry possibility. What grows from them remains to be seen. There is a concept in astrobiology called panspermia, the idea that life itself might travel between worlds, seeding new planets with living organisms rather than mere chemistry. The strong version of this hypothesis imagines bacteria or spores surviving the journey through interstellar space, shielded inside rocks or ice, eventually landing on a hospitable world and establishing a new biosphere. Evidence for such transfer remains elusive, and the challenges of surviving millions of years of cosmic ray exposure, vacuum and temperature extremes are formidable. But there is a weaker version of panspermia that these objects support directly. Call it molecular panspermia, or pseudo-panspermia. In this picture, it is not life that travels, but the chemical ingredients for life. Organic molecules formed in one region of the galaxy are transported to another, enriching the starting conditions for local origin of life experiments. A planet that might have taken 1 billion years to synthesize its own amino acids receives them as gifts from interstellar space, skipping ahead in the sequence of chemical evolution. The Murchison meteorite and other carbonaceous chondrites provide terrestrial evidence for this process. The amino acids and other organics they contain are isotopically distinct from terrestrial compounds, proving their extraterrestrial origin. If a single meteorite can deliver 90 different amino acids to Earth, imagine what an entire population of organic bearing icy objects could deliver over the 4.5 billion year history of the solar system. The numbers are staggering. The cumulative influx of prebiotic material could easily exceed the entire mass of organic carbon currently present in Earth's biosphere. This realization places the question of life's origin in a new context. It is not enough to ask what chemical reactions occurred on early Earth. We must also ask what chemical inventory Earth inherited from its cosmic environment. The planet did not begin as a blank slate. It began with a dowry of organic compounds delivered by impacts, a starting kit assembled over millions of years from material that had itself travelled through the galaxy. The two icy objects detected tens of thousands of light years away are distant cousins of the bodies that delivered Earth's organics. They belong to the same galactic population, the same reservoir of frozen chemistry that has been circulating through the Milky Way since its earliest epochs. By studying them, we study our own origins at one remove, examining the raw materials from which the chemistry of life was eventually assembled. And this is perhaps the deepest significance of the discovery. It connects us to the cosmos in a way that transcends mere observation. We are not passive witnesses to the universe. We are participants in its chemistry, products of reactions that began in stellar nurseries and continued on frozen surfaces drifting through interstellar darkness. The organic molecules in our cells have ancestors, molecular lineages that trace back to the cold clouds where stars were born. The atoms in our bodies have travelled farther than we can easily imagine, crossing the galaxy, changing forms, eventually finding their way into the particular arrangement that allows us to contemplate their journey. The exiles carry more than seeds. They carry our history, written in bonds between carbon and hydrogen, oxygen and nitrogen. And as we learn to read that history, we learn something about ourselves. Theories on the table. When confronted with an object that defies classification, scientists do what they have always done. They speculate, they propose, they test ideas against evidence, discarding those that fail and refining those that survive. The two mysterious icy objects detected by Akari and confirmed by ALMA have generated no shortage of hypotheses, each attempting to explain the peculiar combination of features that makes these objects so difficult to categorize. Let us examine the leading theories one by one and weigh them against what we actually know. The first hypothesis proposes that these objects are remnants of ancient planetary collisions. When two large bodies collide at high velocity, the impact can vaporize rock, melt ice, and send debris streaming into space at speeds sufficient to escape the gravitational pull of the parent system. The Moon is thought to have formed from such a collision, the aftermath of a Mars-sized body striking the early Earth. Similar events must occur throughout the galaxy, wherever planetary systems evolve through chaotic gravitational interactions. In this scenario, the objects we observe are fragments of destroyed worlds, chunks of mantle or crust mixed with ice and organic material, processed by the shocks of the collision itself and launched into interstellar space. The high silicon monoxide abundance would be explained by the vaporization of silicate rock during the impact. The organic ices would be remnants of the pre-collision bodies, preserved in fragments that cooled quickly after ejection. The lack of surrounding dust would result from the violent processing that destroyed most of the original grain population. This hypothesis has appeal. It explains the shock signatures naturally, since planetary collisions are among the most energetic events in any stellar system. It connects the objects to a known process, since we have ample evidence that such collisions occur. And it predicts a population of wandering debris throughout the galaxy, which is consistent with the discovery of two such objects in a single survey. But there are difficulties. The sizes of these objects, hundreds to 1,000 astronomical units, are far larger than what we would expect from collision debris. The Moon, formed from the debris of a planetary impact, is less than 4,000 kilometers in diameter. Cometary fragments are typically measured in kilometers or tens of kilometers. To produce structures the size of these objects through collision would require an impact of extraordinary scale, perhaps the complete destruction of a super-Earth or a mini-Neptune, events that should be exceedingly rare. The second hypothesis proposes that these objects are failed stellar systems, the remnants of cloud cores that began to collapse but never accumulated enough mass to form a star. Brown dwarfs, which straddle the boundary between planets and stars, form through exactly this process. They condense from small pockets of gas and dust, contracting under gravity until they reach a stable configuration supported by electron degeneracy pressure. Some brown dwarfs form in isolation, never joining a stellar system, drifting through the galaxy as free-floating objects. Could these icy objects be extreme examples of this process, structures that began to collapse but were interrupted before reaching even brown dwarf densities? Perhaps a passing star disrupted the collapse, or the core simply ran out of material before reaching critical mass. In this scenario, the objects would be primordial, dating from the era of their formation, carrying chemistry that has been frozen in place ever since. The difficulty here lies in the observed properties. Brown dwarfs, even the coldest and least massive, show thermal emission from their contracting cores. They glow in the infrared, radiating the heat of gravitational contraction. These objects show no such emission. Their spectral energy distributions are dominated by ice absorption, not thermal radiation. If they are failed stellar systems, they have cooled to the point of invisibility, which would require timescales far longer than the age of the galaxy for objects of this size. The third hypothesis proposes that these objects are edge-on-disk systems, structures with a dense central plane that absorbs background light and a diffuse envelope that emits the observed molecular lines. Young stellar objects often possess such disks, flattened structures of gas and dust left over from the star formation process. Viewed edge-on, these disks can produce deep absorption features as background or embedded light passes through the dense midplane. In this scenario, the objects would not be isolated at all. They would be associated with some kind of central source, perhaps a very low-mass star or brown dwarf, that powers the disk and drives the observed shock chemistry. The lack of detected thermal emission would be explained by the geometry. The disk mid-plane blocks our view of the central object, while the cool outer layers produce the ice absorption. This hypothesis is intriguing because it connects the objects to familiar structures. Protoplanetary disks are well studied, and their physics is reasonably well understood. If these are edge-on disks, many of their peculiar properties become explicable. The compact gas emission would arise from the disk atmosphere. The shock signatures would result from accretion or outflow activity. The size scale would be consistent with large, extended disks, around low-mass objects. But here too there are problems. The ALMA observations did not detect any continuum emission from a central source. If there is a star or brown dwarf at the center of these structures, it is either extraordinarily faint or completely obscured. Moreover, the objects are not located in any known star-forming region. Edge-on disks are common around young stellar objects, but young stellar objects are found in stellar nurseries, not drifting in isolation tens of thousands of light-years from the nearest molecular cloud. A fourth hypothesis, more speculative than the others, proposes that these objects represent a genuinely new class of interstellar structure, something that does not fit neatly into existing categories. In this view, the failure of conventional explanations is not a puzzle to be solved, but a signal to be heeded. Perhaps the galaxy contains objects that form through processes we have not yet recognized, evolve through pathways we have not yet modeled, and exist in configurations we have not yet imagined. This hypothesis is, by its nature, difficult to test. It amounts to an admission of ignorance, a statement that current theoretical frameworks are incomplete. But admissions of ignorance have historically been productive in science. The recognition that something does not fit is often the first step toward discovery. Pulsars were initially classified as LGM, for little green men, because their regular radio pulses defied explanation. Gamma-ray bursts were mysterious for decades before their origin in collapsing massive stars and neutron star mergers was understood. Dark matter and dark energy remain named primarily for our ignorance of their true nature. Perhaps these icy objects will eventually receive proper names after we understand what they are and how they form. For now, they exist in a liminal space, neither one thing nor another, challenging us to expand our conceptual frameworks. The research team led by Takashi Shimonishi has been appropriately cautious in their published work. They note that the objects may represent a new class of interstellar icy objects, but they do not claim certainty. They propose future observations with the James Webb Space Telescope and additional ALMA campaigns to better characterize the objects and constrain the range of possible explanations. This is how science proceeds, through careful accumulation of evidence, gradual elimination of hypotheses, and patient refinement of understanding. What can we say with confidence? The objects are real. Their chemical signatures are genuine. They exist in isolation, far from any known star-forming region. They carry ices rich in organic molecules. They show evidence of shock processing. They do not match any existing category of interstellar object. Beyond these facts, we enter the realm of interpretation, where multiple hypotheses compete, and none has yet achieved dominance. There is value in this uncertainty. It means that the discovery is not yet closed, that there is more to learn, that future observations may reveal surprises. The history of astronomy is filled with objects that resisted explanation for years or decades before yielding their secrets. These icy wanderers may join that tradition, remaining mysterious long enough to inspire new generations of researchers to take up the puzzle. In the meantime, the theories remain on the table: collision debris, failed stellar systems, edge-on disks, a new class of object. Each has strengths and weaknesses. Each makes predictions that can, in principle, be tested. The ultimate arbiter will be the data, the photons and radio waves collected by telescopes, pointed at these distant frozen enigmas. What we can say with certainty is that the universe has presented us with something unexpected. In the grand catalogue of cosmic objects, 2 new entries have been added, entries that do not fit the existing taxonomy. Whether they will eventually be filed under a known category, or will require the creation of an entirely new one, remains to be seen. But the fact that such objects exist, that they carry the chemistry of life through the emptiness of space, that they have drifted for millions or billions of years in isolation, this much is no longer theory. It is observation. And observation is where all understanding begins. There is a 5th possibility that hovers at the edges of serious discussion, one that scientists mention reluctantly and usually with qualifications. Could these objects have origins that we cannot currently imagine, not because our instruments are insufficient, but because our assumptions are flawed? The history of astronomy includes numerous cases where unexpected observations were eventually explained by unexpected phenomena. The acceleration of the universe, attributed to dark energy, was not predicted by any mainstream theory before its discovery. The cosmic microwave background radiation, the afterglow of the Big Bang, was initially mistaken for antenna noise. When we look at these icy objects and find no satisfactory explanation, we face a choice. We can assume that one of our existing hypotheses is correct, and that future data will reveal which one. or we can remain open to the possibility that something fundamentally new is at work, something that will require revision of our understanding rather than mere extension of existing frameworks. The honest answer is that we do not know which path will prove correct. The history of science offers examples of both. Some mysteries dissolve quickly once the right observation is made. Others persist for decades, resisting explanation until a paradigm shift reframes the entire question. There is no way to predict in advance which category a given mystery will fall into. What we can do is continue to observe, continue to theorize, and continue to test. The JWST observations that Shimonishi and his colleagues have called for will provide new constraints on the chemical composition and physical structure of these objects. Additional ALMA observations could map the gas distribution at higher resolution, revealing whether there are internal structures that current data cannot resolve. Surveys like SphereX, now actively scanning the sky, may detect more such objects, building a statistical sample that allows us to distinguish between formation scenarios. Each new datum narrows the space of possibilities. Each observation eliminates hypotheses that cannot accommodate it. This is the grinding, incremental work of science, far less dramatic than popular accounts suggest, but far more reliable. Whatever these objects are, we will eventually know. The only question is how long the journey to understanding will take and what surprises await us along the way. For now, the theories remain on the table, each awaiting its day in court. The jury is the universe itself, and its verdict will come in the form of light, of radio waves, of spectral signatures that reveal what words cannot describe. We have only to keep watching, keep listening, and keep asking the questions that these frozen wanderers have placed before us. The mystery endures, and in its endurance lies the vitality of scientific inquiry. We do not yet understand what we have found, but we know that we have found something worth understanding, and that, in the end, is enough to keep the search alive. The cosmic crime scene picture, a detective arriving at a crime scene days after the event. The perpetrator is long gone. The witnesses have scattered. The only evidence consists of traces, residues, patterns in the dust that hint at what transpired. This is the situation facing astronomers who study these mysterious icy objects. Something happened to them, something violent enough to shatter dust grains and release silicon monoxide into the gas phase. But the event itself occurred somewhere else, sometime in the past, and all we have now are the molecular fingerprints left behind. Forensic astronomy is not a formal discipline, but it might as well be. The techniques astronomers use to reconstruct cosmic events share much in common with those used to solve crimes. Both involve working backward from present observations to past causes. Both require understanding the physics of transformation, how evidence degrades over time, what signatures persist and what fades. Both demand imagination constrained by logic, the ability to envision scenarios that fit the evidence without inventing scenarios that contradict it. The crime scene in this case spans hundreds to thousands of astronomical units, a volume of space that could swallow our entire solar system several times over. Within this volume, we find ice absorbing background light at specific wavelengths, gas emitting at specific frequencies, and an absence of dust continuum that tells us something important is missing. The evidence is sparse but definitive. These objects have been processed. The question is how. Start with the silicon monoxide. As we discussed earlier, silicon in the interstellar medium is almost entirely locked in solid dust grains. Liberating it into the gas phase requires shock velocities of at least 10 kilometers per second, with more complete destruction occurring at higher velocities. The ratio of silicon monoxide to carbon monoxide in these objects implies that a substantial fraction of the original dust population was destroyed, releasing its silicon into the surrounding gas. How long ago did this occur? This is where the forensics become challenging. Silicon monoxide in the gas phase does not persist indefinitely. Over time, it reacts with other species, accreting back onto dust grain surfaces, being incorporated into new solid particles. The timescale for this reaccretion depends on the local density and temperature, parameters that are poorly constrained for these objects. In a typical molecular cloud, silicon monoxide might survive for tens of thousands of years before being removed from the gas phase. In the lower density environment of the interstellar medium, it might persist for millions of years. If the shock event occurred millions of years ago, the objects have travelled a considerable distance since then. At velocities of tens of kilometers per second, 1 million years of travel would cover several parsecs, enough to carry an object far from its site of origin. The crime scene we observe today is not where the crime occurred. It is a mobile scene, a ship carrying evidence of a storm encountered long ago in distant waters. The ice features provide complementary information. Water, carbon dioxide, carbon monoxide, methanol and cyanate compounds were all detected in absorption against background or embedded sources. These ices did not form in the interstellar void. They condensed in some denser, colder environment where atoms could freeze onto grain surfaces and build up molecular mantles layer by layer. The presence of methanol and cyanate compounds suggests that some surface chemistry occurred, reactions that require mobility of atoms on grain surfaces or energy input from radiation or cosmic rays. The absence of dust continuum emission is perhaps the most puzzling piece of evidence. In most astrophysical environments, where there are ices, there is also dust. The two go together. Ices form on dust grain surfaces, building up mantles that can be several times thicker than the original grain. When we observe ice absorption, we normally also see thermal emission from the dust that carries the ice, a continuum signal at submillimeter and millimeter wavelengths that traces the solid particle population. These objects show ice absorption, but no dust emission. Several explanations are possible. The dust might be so cold that its thermal emission falls below detection limits. The dust might be so processed by shocks that only the largest, coldest grains survive, emitting at wavelengths longer than ALMA can detect. Or the dust might be genuinely depleted, destroyed by the same shocks that release the silicon monoxide, leaving behind only a sparse population of survivors coated in ice. The third explanation is the most consistent with the overall picture. If shocks destroyed a significant fraction of the dust, they would release both silicon into the gas phase and would reduce the total dust mass available to emit continuum radiation. The surviving grains, fewer in number, would produce weaker continuum emission. If the destruction was efficient enough, the continuum might drop below detection thresholds entirely. But here is the forensic puzzle. If shocks destroyed the dust, they should also have destroyed the ices. Ice mantles are fragile. They sublimate at temperatures above roughly 100 Kelvin, far below the temperatures reached in strong shocks. A shock capable of sputtering silicon from grain cores should certainly be capable of vaporizing the ice that coats those cores. Yet we observe ice features. The ices survived, or they reformed after the shock processing. Reformation is possible if the shock occurred in a relatively dense environment. Atoms released into the gas phase could freeze back onto surviving grain surfaces over timescales of thousands to millions of years. Water, carbon dioxide, and other simple molecules would condense first, followed by more complex species as surface chemistry proceeded. The ice features we observe today might be second-generation ices, formed after the shock event rather than surviving through it. This scenario has interesting implications. Second-generation ices would have a different composition than first-generation ices, reflecting the chemistry of reformation rather than the chemistry of initial condensation. Comparing the detailed molecular abundances of these objects with those of quiescent clouds might reveal signatures of this reformation process, subtle differences in isotopic ratios or molecular ratios that betray their post-shock origin. The line widths of the gas emission provide another forensic clue. Both carbon monoxide and silicon monoxide show velocity dispersions of 8 to 14 kilometers per second. This is broader than thermal line widths at the low temperatures expected for these objects, indicating that bulk motion contributes to the observed profiles. Several mechanisms could produce such broadening. Turbulence is one possibility. If the gas within these objects is turbulent, with eddies and flows moving at several kilometers per second, the superposition of many velocities would broaden the observed lines. Turbulence could be a relic of the original shock event, kinetic energy injected during processing that has not yet dissipated. In the low-density interstellar medium, turbulent dissipation timescales can be very long, allowing turbulence to persist for millions of years. Outflow is another possibility. If material is expanding away from some central disturbance, the approaching and receding sides of the flow would produce redshifted and blue-shifted emission that blend together into a broad line profile. Outflows are common in young stellar objects, driven by accretion and magnetic fields. If these objects contain hidden central sources, even very low mass ones, outflow activity might explain the observed kinematics. Rotation is a third possibility. If these objects are disk-like structures seen at an inclination, rotation would produce velocity gradients across the emitting region. The integrated line profile would then reflect the range of rotational velocities, producing line widths that exceed thermal broadening. This interpretation connects to the edge-on-disk hypothesis discussed earlier. The forensic evidence does not yet distinguish definitively between these possibilities. Higher resolution observations capable of spatially resolving the gas distribution would help. If the broad lines arise from turbulence, the emission should appear uniform across the object. If they arise from outflow or rotation, there should be systematic velocity gradients, approaching gas on one side and receding gas on the other. There is one more piece of evidence that has not received much attention but may prove important. The two objects, despite appearing close together on the sky, are moving in completely different directions. One has a radial velocity of negative 27 kilometers per second, indicating motion toward us. The other has a radial velocity of positive 31 kilometers per second, indicating motion away from us. They are not gravitationally bound to each other. They are not fragments of a common parent body. They are independent wanderers whose apparent proximity is a projection effect, a cosmic coincidence that places them along the same line of sight as seen from Earth. This coincidence is itself interesting. Finding two such rare objects in the same small patch of sky suggests either extraordinary luck or a higher population density than we might otherwise assume. If these objects are common, we should expect to find more of them as surveys continue. If they are rare, their co-location on the sky requires explanation, perhaps a common origin in some ancient event that ejected both objects in different directions. The cosmic crime scene remains open. The detective work continues. Each new observation adds a piece to the puzzle, constraining possibilities, eliminating hypotheses, gradually revealing the sequence of events that produced these frozen wanderers. We may never identify the perpetrator with certainty, never pinpoint the exact moment when shock waves tore through these structures and released their silicon into the void. But we can reconstruct the aftermath, trace the consequences, and learn from the evidence what processes shaped these objects and set them on their lonely journeys. The universe keeps its secrets well, but not forever. With patience and persistence, with ever more sensitive instruments and ever more sophisticated analysis techniques, we pry those secrets loose. The icy objects drifting through the darkness have stories to tell. We're only beginning to learn how to listen. Consider what additional evidence might crack the case. Spectroscopy at higher resolution could reveal the detailed isotopic composition of the detected molecules. Isotope ratios carry information about nucleosynthetic history, about which stars produce the atoms now frozen in these ices. Carbon-12 to carbon-13 ratios, oxygen-16 to oxygen-18 ratios, nitrogen-14 to nitrogen-15 ratios, each traces different aspects of stellar processing and interstellar chemistry. If these objects formed from material processed by a particular generation of stars, their isotopic signatures would reflect that heritage. Polarimetry could reveal the presence and orientation of magnetic fields within these structures. Magnetic fields play crucial roles in star formation, in shock dynamics, and in the alignment of dust grains. If these objects carry remnant magnetic fields from their formation or processing, polarized emission would betray their presence. The orientation of the polarization would indicate the field geometry, whether organized in a coherent pattern or scrambled by turbulence. Time domain observations could reveal variability, changes in brightness or spectrum that would indicate ongoing activity. If these objects contain hidden central sources, even very low mass ones, accretion events might produce detectable flares. If they are undergoing slow dynamical evolution, changes might be detectable over timescales of years or decades. Even null results would be informative, placing upper limits on the level of activity and constraining models of internal structure. The forensic investigation also benefits from context. These two objects are not the only unusual infrared sources in the galaxy. Other surveys have identified candidate objects with similar spectral characteristics, ice absorption without obvious stellar counterparts, located in regions far from active star formation. A systematic search through archival data might reveal additional members of this population, building a sample large enough for statistical analysis. Common properties would point toward common origins. Diversity would suggest multiple formation pathways. There is also the broader context of interstellar chemistry. The molecules detected in these objects are not unique to them. Water, carbon dioxide, methanol, and other species are found throughout the interstellar medium, in molecular clouds, in protostellar envelopes, in the atmospheres of planets and moons. Understanding how these molecules form, persist, and transform is a major goal of astrochemistry, with implications ranging from star formation to the origin of life. These wandering icy objects offer a new laboratory for such studies, a place where interstellar chemistry can be examined in isolation, away from the complicating influences of nearby stars. The crime scene, in short, is not just a mystery to be solved, but an opportunity to be exploited. Every clue that helps us understand what happened to these objects also teaches us something about the processes that shape interstellar matter more generally. The forensic investigation serves double duty, answering specific questions about these particular wanderers while advancing general knowledge about the cosmic environment. And so the work continues. Proposals are written, telescope time is requested, data are collected and analysed, hypotheses are tested and revised. Slowly, incrementally, the picture sharpens. The crime scene gives up its secrets one photon at a time, and the detectives of the cosmos grow ever closer to understanding what happened in that distant corner of the galaxy, long ago, when violence touched these frozen travellers and sent them on their way into the dark. JWST and SphereX, the hunt continues. The James Webb Space Telescope floats at a point in space called L2, about 1.5 million kilometres from Earth, on the side opposite the Sun. From this vantage, it looks outward at the universe with the largest and most sensitive infrared eye ever constructed. Its primary mirror, 6.5 meters across, collects light with an area more than 6 times greater than the Hubble Space Telescope. Its detectors, cooled to temperatures just a few degrees above absolute zero, can sense the faintest whispers of infrared radiation from the most distant and coldest objects in the cosmos. When the research team published their findings about these mysterious icy objects in February of 2025, they included a specific recommendation. Follow-up observations with the James Webb Space Telescope could provide crucial new data. The sensitivity and spectral resolution of JWST far exceed what ground-based telescopes or even ALMA can achieve for certain types of observations. In particular, JWST could probe the detailed composition of the ices, identifying minor molecular species that reveal the chemical history of these objects. Think of it this way. Akari detected the broad strokes, the presence of water, carbon dioxide, and other common ices. ALMA mapped the gas emission, revealing carbon monoxide and silicon monoxide in the surrounding material. But neither instrument could perform the detailed spectroscopy needed to identify trace molecules, species present at the level of a few percent or less of the total ice inventory. These trace species are often the most diagnostic, carrying information about specific chemical pathways that the dominant molecules cannot provide. JWST can do this. Its near-infrared spectrograph and mid-infrared instrument can slice the infrared spectrum into thousands of fine channels, revealing absorption features too narrow or too faint for other telescopes to detect. If these icy objects contain amino acids, nucleobases, or other complex organic molecules, JWST has the best chance of finding them. If the ice composition varies between the two objects, suggesting different formation histories or processing environments, JWST can measure those differences with precision. There's also the question of physical structure. ALMA observations revealed that the gas emission is compact, confined to regions less than 1 arc-second across. But at the distance of these objects, 1 arc-second corresponds to a vast physical scale. JWST, with its superior angular resolution in the infrared, could potentially resolve internal structure that ALMA cannot see. Clumps, gradients, asymmetries, all would provide clues to the three-dimensional geometry of these objects and the processes that shaped them. As of today, no JWST observations of these specific objects have been publicly announced. The telescope's observing schedule is set through a competitive proposal process, with scientists from around the world submitting requests for time. The demand far exceeds the supply. Only a fraction of proposed observations are approved, and priority goes to projects judged to have the highest scientific impact. Whether the icy object team has submitted a proposal, and whether that proposal has been accepted, remains unknown to the public. But even if JWST does not observe these particular objects, other telescopes continue the hunt. Ground-based facilities with adaptive optics can achieve remarkable resolution, compensating for the blurring effects of Earth's atmosphere. The Very Large Telescope in Chile, the Keck Observatory in Hawaii, the Gemini telescopes in both hemispheres, All have instruments capable of probing infrared sources with high sensitivity. Archival data from past observations may contain unrecognized signatures of similar objects, waiting to be identified through careful reanalysis. And then there is Spherex, the spectrophotometer for the history of the universe, epoch of Ryonisation and ICE's explorer, launched on March 11th of 2025, just weeks after the icy object discovery was published. This NASA mission is designed to survey the entire sky in infrared light, measuring the spectra of hundreds of millions of objects over its 2-year primary mission. One of its core scientific objectives is to map the distribution of interstellar ices across the Milky Way. Spherex is not designed for deep targeted observations like JWST. It is a survey instrument, trading depth for breadth, scanning the entire celestial sphere rather than staring at individual targets. But this approach has its own advantages. A survey can find objects that nobody thought to look for, sources that do not appear in any existing catalogue, anomalies that stand out only when compared against millions of normal stars and clouds. If icy objects like those detected by Akari exist in significant numbers, Spherex should find them. Its infrared detectors are sensitive to the same ice absorption features that revealed the original objects. Its all-sky coverage ensures that no corner of the galaxy is missed. Over the course of its mission, Spherex will build a census of interstellar ices more complete than anything previously available, a database that future astronomers can mine for decades. The timing is almost poetic. The discovery of these mysterious objects was announced in late February. Spherex launched in early March. The instrument designed to survey interstellar ices across the galaxy began its work just as we learned that wandering icy objects might be more common and more strange than anyone suspected. The universe handed us a puzzle and simultaneously handed us a tool for solving it. What might Spherex find? At minimum, it should detect more objects with ice absorption features in unexpected locations, sources that do not fit the standard categories of stars, clouds, or protostars. Some of these will turn out to have mundane explanations, edge on disks or background sources with confusing spectra, but others may prove to be genuine additions to the population of mysterious wanderers, new data points that help constrain how these objects form and evolve. At maximum, Spherex could reveal an entire hidden population, dozens or hundreds of icy objects scattered across the galaxy, drifting through the void, carrying their frozen cargo of water and organics. If this population exists, it has implications that ripple through multiple fields of astrophysics. It would change our understanding of the interstellar medium, revealing it as a place where organized structures can persist far from star-forming regions. It would change our understanding of cosmic chemistry, showing that organic bearing ices can survive indefinitely in the harsh environment between stars. It would change our understanding of how the ingredients of life are distributed across the galaxy, demonstrating that prebiotic molecules are not confined to the immediate neighborhoods of stars. There is a rhythm to scientific discovery that repeats across centuries and disciplines. First comes the unexpected observation, the anomaly that does not fit existing categories. Then comes the scramble to explain, the proliferation of hypotheses, the debates between competing interpretations. Then comes the era of systematic study, the deployment of new instruments designed to probe the anomaly in depth, the accumulation of data that eventually resolves the mystery. We are at the transition between the second and third phases now. The anomaly has been observed, the hypotheses have been proposed, the instruments are coming online. JWST and Spherex are not the only tools in the arsenal. ALMA continues to operate, and future observations with different configurations could provide new constraints on the gas properties of these objects. The upcoming extremely large telescope, currently under construction in Chile, will have unprecedented sensitivity and resolution in the infrared, potentially capable of resolving the internal structure of distant icy bodies. Radio telescopes operating at longer wavelengths could search for molecular species not accessible to infrared instruments, building a more complete chemical inventory. Each new observation narrows the range of possibilities. Each new datum eliminates hypotheses that cannot accommodate it. The process is slow, measured in years rather than months, but it is inexorable. Given enough time and enough data, the nature of these objects will become clear. Whether they are collision debris, failed stellar systems, edge on disks, or something entirely new, the answer is encoded in the light they emit and absorb. Our task is simply to collect that light and decode its message. The hunt continues because the quarry is worth pursuing. These are not merely strange objects. They are potential windows into cosmic processes that shape the distribution of matter and chemistry across the galaxy. They are possible vehicles for the transport of life's ingredients between stellar systems. They are challenges to our current understanding, anomalies that demand explanation, and in demanding explanation push the boundaries of what we know. Somewhere out there, drifting in the darkness, more frozen wanderers await discovery. Spherex is looking for them even now, its detectors scanning the sky, its spectrographs measuring the subtle dips in brightness that reveal the presence of ice. JBST stands ready to scrutinize any promising candidate in detail, and astronomers around the world are analyzing data, writing proposals, planning the next observations that will advance our understanding. The hunt is not a solitary pursuit. It is a collective endeavor, a global collaboration of scientists and instruments and ideas. The mysterious icy objects do not belong to any one team or any one nation. They belong to the cosmos, and the cosmos belongs to all of us. In seeking to understand them, we participate in an ancient human activity, the quest to know what lies beyond the familiar, to map the unknown, to name the nameless. The answers will come. They always do, eventually. And when they do, we will have learned something new, not only about these particular objects, but about the universe that contains them, and about ourselves as creatures capable of asking such questions and finding such answers. There is a practical dimension to this hunt that deserves mention. Finding more icy wanderers is not merely an academic exercise. If these objects are common, they represent a resource, a reservoir of water and organic molecules distributed throughout the galaxy. For future space exploration, for the long-term settlement of other worlds, water is precious. Every kilogram that can be sourced locally is a kilogram that does not need to be launched from Earth at enormous expense. Asteroids and comets in our own solar system already figure in plans for space resource utilization. But those bodies are gravitationally bound to the Sun, confined to orbits that keep them nearby, but also make them part of a complex dynamical environment. Interstellar icy objects represent a different kind of resource. Wanderers that pass through stellar systems on hyperbolic trajectories, briefly accessible before continuing their endless journey. If such objects are abundant, they might occasionally pass through our own solar system. Oumuamua and Borisov proved that interstellar visitors do arrive. Most pass too quickly to be studied in detail, but occasionally one might approach slowly enough, or closely enough, to be intercepted. A mission to sample an interstellar icy object would return material from another stellar nursery. Chemistry that formed light years away and billions of years ago. The scientific value would be immense. Spherex and its successors may help identify where such objects are most likely to originate. By mapping the distribution of interstellar ices across the galaxy, these surveys create a kind of weather map for the cosmic environment. Regions dense with icy objects would be regions where ejection events are common, or where formation of isolated icy bodies is efficient. Understanding this distribution helps predict the flux of interstellar visitors through our own neighborhood. There is also the question of planetary defense. Objects passing through the inner solar system on interstellar trajectories are, almost by definition, moving fast. They approach and recede in months rather than years. If one were on a collision course with Earth, warning time would be short. The more we understand about the population of interstellar objects, the better we can assess this risk and prepare for it. Most such objects are small and harmless, but the discovery of larger icy bodies in interstellar space reminds us that the size distribution extends upward, possibly to objects large enough to cause significant damage. These practical considerations complement the scientific ones. The hunt for icy wanderers is both a quest for knowledge and a reconnaissance of the environment in which our civilization must learn to thrive. Each discovery advances both goals, teaching us about the cosmos while preparing us to live in it. And so the telescopes scan, the spectrographs measure, the data flow into computers around the world. The hunt continues not because we must, but because we can, because the tools exist, because the questions beckon, because the night sky holds mysteries that reward those who study them. The frozen wanderers are out there, carrying their secrets through the dark. We are learning to find them, and in finding them, to understand a little more about the universe that made us all. A universe full of strangers. We grew up thinking we understood the cosmic inventory. Stars, planets, moons, asteroids, comets, dust, gas. These were the components of the universe, the building blocks, from which everything else was assembled. Textbooks presented clean taxonomies, neat categories into which every object could be sorted. If something did not fit, that was a problem with our observations, not with our categories. The past few decades have dismantled this comfortable picture. Every year brings discoveries that challenge our classifications, objects that blur boundaries, or exist in gaps we thought were empty. Hot Jupiters orbit their stars in days rather than years. Super-Earths occupy a size range that our own solar system skipped entirely. Free-floating planets drift between stars unbound to any sun. Brown dwarfs blur the line between star and planet. Interstellar visitors like Oumuamua challenge our assumptions about what can travel between stellar systems. The mysterious icy objects discovered by Akari and confirmed by ALMA are the latest additions to this parade of strangers. They fit no existing category. They obey no familiar template. They simply exist, demanding that we expand our mental frameworks to accommodate them. This is what it means to live in a universe full of strangers. Every time we develop new instruments or survey new regions of parameter space, we find things we did not expect. The universe is not obligated to conform to our categories. It presents whatever it presents, and we must adjust. Consider the history of interstellar object detection. Before 2017, no object from outside our solar system had ever been definitively identified. We assumed such objects must exist. Planetary formation is messy, and material should occasionally be ejected into interstellar space. But detection was considered nearly impossible. The objects would be small, dark, fast-moving, and incredibly rare. Finding one would be like spotting a single grain of sand blown across a desert. Then Oumuamua appeared. Discovered by the Pan-STARRS survey in Hawaii, it was initially classified as a comet, then reclassified as an asteroid when it showed no cometary activity. Its elongated shape, its peculiar acceleration, its mysterious silence to radio telescopes all generated controversy. Was it a fragment of a larger body? A shard of frozen nitrogen? Something even stranger? The debates continue to this day, because Oumuamua passed through too quickly for definitive study. It came and went, leaving more questions than answers. 2 years later, Borisov arrived. This one was unmistakably a comet, outgassing vigorously as it approached the sun. Spectroscopy revealed water, carbon monoxide, and other familiar volatile species. Borisov looked almost exactly like comets from our own Oort cloud, suggesting that the processes that form comets are similar throughout the galaxy. The strangeness of Oumuamua was balanced by the familiarity of Borisov. Perhaps interstellar visitors come in many varieties, some exotic and some mundane. The icy objects detected tens of thousands of light years away extend this story in new directions. They are not passing through our solar system. We cannot collect samples or send spacecraft to intercept them. We see them only as faint infrared sources, their presence inferred from the light they absorb and emit. Yet they tell us something profound about the diversity of interstellar material. If such objects exist in abundance, the space between stars is not empty. It is populated by a hidden census of wanderers, each carrying its own cargo of ice and chemistry. What else might be out there? The icy objects join a growing list of cosmic strangers that have emerged from the shadows in recent years. Consider the following examples. In 2020, astronomers announced the discovery of a black hole just 1,000 light-years from Earth, the closest known to our solar system. It was found not by its own radiation, but by its gravitational effect on a companion star. The companion's orbital motion revealed the presence of an unseen massive object, later confirmed as a stellar mass black hole. If such objects exist so close to us, undetected until now, how many more lurk in the darkness? In 2021, the discovery of a population of primordial black holes was proposed to explain certain gravitational wave signals. These would be black holes formed not from collapsed stars but from density fluctuations in the early universe, relics of the Big Bang itself. If primordial black holes exist, they could account for some or all of the dark matter that pervades the cosmos. The universe might be teeming with invisible gravitational wells, bending space and time around them, detectable only through their subtle effects on passing light. In 2023, the JWST revealed galaxies at extreme redshifts that appeared more massive and more evolved than existing models predicted. These two early galaxies challenged our understanding of cosmic history, suggesting that structure formation proceeded faster than theorists expected. The universe, it seemed, had secrets even in its earliest epochs, surprises that awaited only the development of sufficiently powerful telescopes. Each discovery recalibrates our sense of what is possible. Each stranger forces us to revise our census of cosmic objects. The icy wanderers are part of this ongoing expansion of the known. One more category to add to the inventory, one more type of object to consider when we ask what the universe contains. There is a philosophical dimension to this pattern. Every taxonomy is a human construction, a way of organizing observations that reflects our cognitive needs as much as objective reality. We draw boundaries because our minds work with categories. We name things because naming is how we claim understanding. But the universe predates our categories and will outlast them. It contains what it contains, indifferent to whether we have names for it. The discovery of objects that resist classification is therefore a kind of gift. It reminds us that understanding is provisional, that our maps are not the territory, that there is always more to learn. Scientists sometimes speak of the known knowns, the known unknowns, and the unknown unknowns. The icy wanderers moved from the third category to the second. We now know that such objects exist. We do not yet know what they are. This progression is the essence of discovery. What unknown unknowns remain? By definition, we cannot say. But history suggests that the list is long. Every generation of astronomers has believed itself close to a complete picture, and every generation has been humbled by what came next. The steady-state universe gave way to the Big Bang. The static galaxies gave way to an expanding cosmos. The lonely Earth gave way to thousands of confirmed exoplanets. Each transition seemed unimaginable until it happened, and then it seemed obvious. The strangers we meet in the cosmos teach us humility. They teach us that reality is larger than our imagination. They teach us that the universe is under no obligation to be simple, or convenient, or comprehensible at first glance. And yet, paradoxically, they also teach us that the universe is comprehensible in the end. Every stranger we have encountered has eventually yielded its secrets. Pulsars were explained as rotating neutron stars. Quasars were explained as accreting supermassive black holes. Gamma-ray bursts were explained as collapses and neutron star mergers. The strangers become familiar once we learn their language. The icy wanderers will join this procession. Today they are mysterious. Tomorrow or next year or next decade they will be understood. We will know how they form, how they evolve, how they fit into the broader ecology of interstellar matter. And when we know, we will look back on our current puzzlement with the same bemused recognition that we now apply to earlier mysteries. But for now, the strangeness is real. For now, we stand at the edge of the known, looking out at objects that do not yet have names, processes that do not yet have explanations. This is the frontier, the place where science is most alive, where every observation might overturn expectations and every theory is provisional. The universe is full of strangers. We have met two of them, frozen and silent, drifting through the void 40,000 light-years away. They will not be the last. The night sky contains multitudes, most still waiting to be discovered, all waiting to be understood, and we, the curious inhabitants of a small planet orbiting an ordinary star, continue the ancient work of meeting them, one by one, and learning their names. There is comfort in this process, a kind of existential reassurance. The universe may be vast and strange, but it is knowable. The strangers may arrive unexpected, but they can be studied, measured, understood. Every mystery eventually becomes knowledge. Every frontier eventually becomes familiar territory. The expansion of the known is a one-way process, a ratchet that only moves forward, accumulating understanding with each generation of observers. The icy wanderers remind us of something else as well. They remind us that we are not separate from the cosmos, but embedded in it. The atoms in our bodies were forged in stars. The water in our cells may have arrived on primordial comets, perhaps on objects not unlike these distant wanderers. The organic molecules in our tissues connect us to the interstellar chemistry that pervades the galaxy. We are not observers looking at the universe from outside. We are part of the universe looking at itself. This perspective transforms the encounter with cosmic strangers. They are not entirely alien, not entirely other. They are distant relatives, products of the same physical laws, built from the same periodic table of elements, participating in the same chemical reactions that gave rise to life on Earth. When we study them, we study our own origins at many removes, tracing the threads that connect a frozen body drifting between stars to the minds that contemplate its existence. The strangers also remind us of time. The icy objects have been travelling for millions or billions of years. They have witnessed the birth and death of stars, the collision and merger of galaxies, the slow evolution of the Milky Way from a younger, more chaotic state to its present relatively orderly spiral structure. They carry information about epochs we cannot directly observe, chemistry that reflects conditions long vanished from the present-day universe. In a sense, they are time capsules, archives drifting through space, waiting for someone to retrieve their contents. Human civilization is young by comparison. We have been building telescopes for only 4 centuries. We have been conducting systematic astronomy for barely 1. The icy wanderers predate not only our science but our species, our genus, our entire evolutionary lineage. They were old when our ancestors were single-celled organisms floating in warm Archean seas. They will continue drifting long after whatever descendants we produce have either spread across the galaxy or vanished entirely. This temporal perspective induces humility. We are temporary witnesses to an ancient cosmos. Our observations capture mere instants in processes that unfold over timescales we can barely imagine. The strangers we encounter have stories longer than human history, journeys that began before life on Earth achieved complexity. To study them is to touch deep time, to connect with a past so remote that it humbles all our pretensions. And yet we do study them. We build instruments and write proposals and collect data and publish papers. We argue about interpretations and design, follow-up observations, and gradually, incrementally advance understanding. The enormity of cosmic time does not paralyze us. It inspires us. Knowing that we are brief makes each discovery more precious, each insight more valued. The universe full of strangers is also a universe full of opportunities. Every object we have not yet understood is a lesson waiting to be learned. Every mystery we have not yet solved is a gift to future generations of scientists. The icy wanderers are part of this gift, a puzzle left by the cosmos for whoever develops the tools to solve it. We may not solve it completely in our lifetimes. That is acceptable. Science is a relay race, with each generation carrying the baton as far as it can before passing it to the next. In the meantime, we live with the wonder. We contemplate objects that defy explanation, and feel not frustration but fascination. We look at the night sky knowing that it contains more than we can see, more than we can understand, more than we can imagine. The strangers are out there, drifting in silence, keeping their secrets for now, ready to reveal them when we are ready to receive. What if we are looking at something entirely new? Let us entertain a possibility that hovers at the edge of scientific respectability. What if these objects are not merely unexplained, but unexplainable within current frameworks? What if they represent something so novel, so unprecedented, that understanding them requires not just new data, but new concepts? Science progresses through 2 distinct modes. Most of the time, it operates within established paradigms, filling in details, extending theories, confirming predictions. This is normal science, the steady accumulation of knowledge within accepted frameworks. But occasionally, anomalies accumulate to the point where the frameworks themselves must change. Old paradigms give way to new ones. Conceptual revolutions transform entire fields. What was once unthinkable becomes obvious in hindsight. The history of astronomy is punctuated by such revolutions. The Copernican revolution displaced Earth from the centre of the cosmos. The discovery that nebulae were distant galaxies expanded the known universe by orders of magnitude. The detection of the cosmic microwave background confirmed the Big Bang and overturned the steady-state model. In each case, observations that did not fit existing theories eventually forced the theories to change. Could these icy objects be harbingers of such a revolution? The question is speculative, perhaps even presumptuous. 2 objects detected in a single survey hardly constitute a crisis for astrophysics, and yet, The failure of every conventional explanation to fully account for their properties is suggestive. When an anomaly resists explanation, when hypothesis after hypothesis falls short, there comes a point when we must consider whether the problem lies not with our specific theories, but with our underlying assumptions. What assumptions might be wrong? Consider the assumption that all macroscopic interstellar structures are either star-forming or the remnants of star formation. This assumption pervades astrophysics. Molecular clouds form stars. Protostellar disks form planets. Stellar winds and supernovae shape the interstellar medium. Every structure is connected to the stellar life cycle, either directly or indirectly. But what if there are structures that exist independently of stars? What if the interstellar medium contains organized features that form, evolve, and persist without any stellar influence? The icy objects might be examples of such autonomous structures, condensations of matter that arose through processes unconnected to star formation, perhaps in the early universe, perhaps in the far outer reaches of the galaxy, perhaps through some mechanism we have not yet identified. This is a radical idea. It challenges assumptions so deeply embedded that they are rarely stated explicitly. But radical ideas are sometimes necessary. The history of science is full of cases where progress required questioning the unquestioned. Consider another assumption, that the interstellar medium is well mixed, that material ejected from one stellar system quickly disperses and blends with the surrounding gas. This assumption underlies our models of galactic chemical evolution, our estimates of molecular abundances, our understanding of how elements spread through the galaxy. But what if some material remains coherent, resisting mixing, preserving its identity across cosmic timescales? The icy objects might be examples of such persistent structures, packages of matter that have maintained their integrity for billions of years, carrying the chemical signature of their formation through an ever-changing galactic environment. If such structures are common, the interstellar medium is more heterogeneous than we assumed, a patchwork of distinct regions rather than a smooth continuum. Consider a third assumption, that we understand all the relevant physics. This assumption is rarely stated because it seems so obvious. Physics is physics. The same laws that operate in laboratories on Earth operate throughout the cosmos. There are no surprises lurking in the equations, and yet we know this assumption is incomplete. Dark matter and dark energy, which together constitute more than 95% of the universe's contents, remain unexplained. We observe their effects, but do not understand their nature. The icy objects almost certainly have nothing to do with dark matter or dark energy, but their existence reminds us that the cosmos contains more than our current physics can fully explain. What might new physics look like in this context? The question invites speculation that ventures beyond the bounds of rigorous science. Perhaps there are forms of matter that interact with ordinary atoms in ways we do not yet understand, clumping and organizing and persisting in configurations our theories do not predict. Perhaps there are energy sources we have not identified, processes that power chemical reactions without the familiar signatures of stellar radiation or shock heating. Perhaps the very structure of space contains features, gradients, or boundaries that affect how matter behaves on large scales. These are wild ideas, more at home in science fiction than science, but they illustrate the range of possibilities when existing explanations fail. The icy objects may eventually yield to conventional analysis, turning out to be unusual but not unprecedented examples of some known phenomenon, or they may require something more, some extension of current knowledge that we cannot yet foresee. There is a methodological lesson here. When confronted with an unexplained observation, scientists must balance two competing impulses. The conservative impulse says to keep looking for conventional explanations, to exhaust known possibilities before invoking unknown ones. This impulse is healthy. It prevents the proliferation of exotic theories to explain every unexplained datum. Most anomalies do eventually find conventional explanations, but the revolutionary impulse also has its place. It says to remain open to the possibility that something genuinely new is happening, that the anomaly might be a signal rather than a puzzle. This impulse is also healthy. It prevents the ossification of paradigms, the refusal to consider alternatives simply because they are unfamiliar. Good science navigates between these impulses. It takes anomalies seriously without jumping to exotic conclusions. It seeks conventional explanations diligently while remaining open to unconventional ones. It accumulates evidence patiently, allowing the data to guide the interpretation, rather than forcing the data into pre-existing categories. The icy objects are receiving exactly this treatment. The research team has proposed conventional explanations, evaluated their strengths and weaknesses, and called for follow-up observations to constrain the possibilities. This is the scientific method at work, careful, systematic, open-minded. Whether the eventual explanation is conventional or revolutionary, the process is the same. But let us linger for a moment with the revolutionary possibility. What if we are looking at something entirely new? What if these objects are the first examples of a previously unknown class of cosmic structures, one that forms through processes we have not yet modelled, evolves through pathways we have not yet imagined, and exists in configurations we have not yet conceived? The emotional resonance of this possibility is powerful. It suggests that the universe still has fundamental surprises in store, that our current understanding, however sophisticated, remains incomplete. It connects the present moment to the great discoveries of the past, when observers encountered phenomena that transformed their fields. It invites us to imagine that we might be witnessing the beginning of a new chapter in astronomy, one whose contents we cannot yet predict. This is romantic thinking, perhaps, more poetry than science. But poetry has its place. The drive to understand the cosmos is not purely rational. It is fueled by wonder, by the sense that the universe is larger and stranger and more beautiful than we can comprehend. The icy objects, whatever they turn out to be, partake of this wonder. They are reminders that the cosmos is not a solved puzzle, but an ongoing revelation. In the end, the question of whether we are looking at something entirely new may be less important than the fact that we are looking at all. The human capacity for curiosity, for sustained attention, for systematic inquiry, is itself remarkable. We did not have to care about frozen objects drifting 40,000 light-years away. Their existence affects our daily lives not at all. But we do care. We build telescopes and analyse spectra and write papers and debate interpretations, all because we want to know. This wanting to know is perhaps the most extraordinary thing about our species. It has driven us from cave paintings to space telescopes, from oral traditions to digital archives, from local myths to cosmic understanding. The icy wanderers are one more object of this ancient wanting, one more mystery that draws our attention outward, one more invitation to learn something we did not know before. Whether the invitation leads to a conventional explanation or a revolutionary one, the journey is worthwhile. The universe has presented us with a puzzle, and we will work to solve it. That is what we do. That is who we are. And in the end, that may be the most important thing these mysterious objects reveal, not about themselves, but about us. There is one final thought to consider. The detection of these objects was, in a sense, accidental. The Akari satellite was surveying the sky for entirely different purposes when it recorded the anomalous infrared sources that would later draw ALMA's attention. The objects were not predicted, they were not sought. They simply appeared in the data, demanding explanation. How many other discoveries await in existing archives hidden in plain sight? Astronomers have accumulated petabytes of observational data over the decades, far more than any human could examine in a lifetime. Algorithms search these archives for patterns, but algorithms can only find what they are programmed to find. Objects that do not match, expected templates may slip through unnoticed, waiting for someone to ask the right question. The icy wanderers suggest that the galaxy contains populations we have not yet imagined. They suggest that our surveys, however comprehensive, have blind spots, categories of objects that our search criteria do not include. As machine learning and artificial intelligence become more sophisticated, we may develop tools capable of finding anomalies that defy categorization, objects that exist in the gaps between our expectations. Each such discovery will pose the same question these objects pose. Is this something we almost understand? A slight variation on known themes? Or is this something genuinely new? A doorway to concepts we have, not yet formulated? The distinction matters, but it cannot be made in advance. Only the patient accumulation of evidence can reveal whether an anomaly is a puzzle to be solved or a paradigm to be shifted. The next few years will bring more data, more analysis, more understanding. Spherex is surveying the sky. JWST is taking spectra. ALMA continues to map molecular emission with ever greater sensitivity. Ground-based telescopes are upgrading their instruments. The networks of observation grow more powerful with each passing year. Somewhere in that flood of data, the answers to our questions are forming. The icy wanderers will yield their secrets, not through sudden revelation, but through gradual constraint, as hypothesis after hypothesis is tested and either confirmed or discarded. The process is slow, but it is reliable. Science works because it demands evidence and respects evidence, because it changes its conclusions when the evidence requires it. And so we wait and watch and wonder. The frozen travellers continue their journeys through the dark, indifferent to our curiosity, carrying their chemical secrets toward destinations we cannot predict. We have glimpsed them briefly, measured what we can, speculated about the rest. The full story remains to be written, by observers not yet born, using instruments not yet designed, guided by theories not yet conceived. Closing. The stars above us tonight appear fixed and familiar, points of light that have guided travellers and inspired poets for millennia. But between those stars, in the vast darkness that separates them, frozen wanderers drift in silence. They carry water and carbon, methanol and cyanides, the raw ingredients of chemistry that could, under different circumstances, give rise to the complexity of life. They have been travelling for longer than our species has existed, will continue travelling long after we're gone. We have seen two of them, briefly, through the sensitive eyes of telescopes separated by light years. We have measured their ice absorption, detected their gas emission, puzzled over their shock signatures. We have proposed theories and eliminated hypotheses and called for more observations. The scientific process continues as it must. But beyond the process, there is the wonder. Wonder that such objects exist. Wonder that we can detect them. Wonder that the universe contains so much more than we assumed. So many strangers waiting to be met. So many secrets waiting to be revealed. Thank you for travelling with me through this exploration of mystery and discovery. If this calm, science-driven format resonates with you, consider subscribing for more journeys into the unknown. And remember, the things we cannot explain are not obstacles to understanding. They are invitations. The content presented here is for educational and entertainment purposes. The scientific findings discussed are based on peer-reviewed research published in the Astrophysical Journal and other reputable sources, but speculation and interpretation are my own and do not represent official scientific consensus. Good night and clear skies.